All right, good day, everybody. Wherever you are, I'm so happy and I'm so excited to be bringing this to you. It's a very, very big package from CMRC, Creative Mind Real Concept. And I'm most privileged to be the innovator, the initiator of this program. It is a very, very big success to bring this to you. Free Success Project 2025. And this year, I am so happy. We have amazing facilitators, persons who are selfless, who are passionate, who are explicit in every ramification of their discipline, and they will blow your mind. So I want you to keep your tabs and start watching these videos and get excellent results and come back to tell us, and we'll rejoice with you. God bless you. Good day, everybody. My name is Folaranmi Israel Olaoluwa. So in this CMRC time like this, I'll be taking you chemistry. So having known that you guys are preparing for JAMB, like UTME, so I am here once again to take you like one of the most important aspects of chemistry, which over time have been repeated in JAMB. So I want to leave like to start with this, that chemistry is not something that is hard. It's very simple. So it's not a hard course. I guess my hard subject as it were. So because by God's grace, I did JAMB too, and I was able to add a 99 in my chemistry. So, and I believe you can do the same. So you can do much better, maybe by having 100 over 100. Right now, we are going to start with nuclear chemistry. So as the name implies, nuclear chemistry, that means you are talking about something that has to do with the nucleus. You know, in an atom, so as a chemistry student, I believe you know that for different elements, we have their atoms. Are you getting me now? And then in an atom, we have like different subatomic particles being present. So in an atom, we have two major particles that are present. So we have like the proton and then the nucleus. In the nucleus, you have the proton and then what? The neutron. So inside the nucleus, you have the protons and then you have the what? The neutron. So you find the electrons revolving around the what? Around the orbit of the atom. So you don't find electron in the nucleus. No. Is revolving around the orbit, that structure of the atom. So, but inside the nucleus, you find what? You find the neutrons, and then you have what? You find the neutrons and the protons. So the protons, they are positively charged particles, positively charged particles. While the neutrons, they have what? They have no charge. They have no charge. So now, by the name nuclear chemistry, that means we are talking about what? The chemistry of the nucleus. So having known that chemistry is about the study of matter, its composition, and any process like that it undergoes. That means in nuclear chemistry, we'll be talking about the chemistry of the nucleus and everything that happens in the nucleus. So this is going to take us into a very important aspect in nuclear chemistry, and which is what? Radioactivity. Which is radioactivity. So by the name, radioactivity is like the spontaneous but disintegration of a nuclei. So with the emission of what? Radiation and energy. That is what radioactivity means. So it's the spontaneous disintegration of a nuclei with the emission of what? Heat. Emission of heat, energy, and what? Radiation. So before I go further, let me define what a nuclide is for you. I mean nuclide, nuclide. So a nuclide is like a characteristic, let me say, atom of an element with what? A respective mass number, and then what? Proton number. So proton number is the same thing as what? Atomic number. So when we are talking about a nuclide, we are just talking about a particular atom with what? Its mass number, and then it's what? Proton number, which otherwise is known as the what? Atomic number. So when we talk about radioactivity, we mean the spontaneous disintegration of that kind of nuclide. Are you getting me now? With the emission of energy and radiation. With the emission of energy and radiation. I don't know whether you've wondered in your physics lab, they ask you guys, they always tell you to put on lab coats. So it's not just for show. It's not just to show that you are a science student. No. It has, that your lab coat that you are wearing has a kind of protection it gives to you when you are working in the lab. So if at all you are exposed to some kind of radiation, so there are some kind of radiation and rays that lab coat is capable of blocking. So when you go to a lab without wearing such a lab coat, I'm sorry to say that You are just exposing yourself to some dangers. All right. So moving on. Under radioactivity, it is divided into like two broad groups. So we have natural radioactivity and then what? Artificial radioactivity. So when we talk about something natural, that means like it can occur like spontaneously by nature, just by chance, just occurring. And then when we are talking about artificial, that means it requires some kind of maybe human effort to make the stuff done. So when you're talking about natural radioactivity, it's like the spontaneous breakdown of a radioactive substance or elements, as it were, so to release some emissions, which you know like radiation, and then what? Energy. So the main thing is that you have a radioactive substance. It breaks down by itself without you doing anything. So it's that radioactive substance breaks down and then what? Emits radiation and then what? Energy. But when we are talking about artificial radioactivity, it is not spontaneous. Why? Because it does not occur by itself. It needs maybe some kind of bombardment. So you bombard a substance that is maybe not radioactive before. So by bombarding it with some subatomic particles, by bombarding it with some subatomic particles, don't forget I mentioned subatomic particles the other time, that they are those particles you find in the nucleus of an atom, and those are the what? Protons and neutrons. So artificial radioactivity occurs when you bombard like elements that are not radioactive before with those subatomic particles, and then after that bombardment they become what? Radioactive, and then they break down. Natural, you don't need anything, it's spontaneous, it occurs like that, it just breaks down, it breaks down. But artificial, you need bombardment. You bombard those substances that are not radioactive before, so they become radioactive and then they what? Break down. So now, when we are talking about radioactive substances, there are those substances that are capable of breaking down like at ease. So, and then what can make that happen, or a characteristic, like a major characteristic of a substance that is going to be radioactive, is the fact that that atom will have like atomic number greater than 83. So when you have an atom that has atomic number, what is atomic number? Number of protons. For example, now let me go back to your 20 element that you know, starting from hydrogen to calcium. You know that hydrogen has atomic number 1. Calcium, which is the last of the 20 elements, has atomic number 20. So when we are talking about radioactive substances, they have atomic number 83 and above. So when you find an atom having that kind of feature, there is tendency for it to be radioactive. So it can undergo natural radioactivity. But there is something that is so unique about the radioactive substances, that they degrade by breaking down. You know, if something breaks down, that means it's decaying, it's degrading. So there's something we call half-life. You can see it here, half-life. So if I say half-life, that means I'm talking about something that is like something breaking down into two. So half-life of a radioactive element is the time taken for that radioactive substance to break down into half of its initial or original value. Is the time taken for a radioactive substance to break down into half of its initial or original value. So now, let's say the mass of, for example, one radioactive element is uranium. Let's say uranium now. So it now breaks down. It has a mass of, let's say, 50 grams currently. So it has a mass of 50 grams. So when it breaks down to 25 grams, which is what? The half of 50, that time it takes to break down from that 50 to 25 is the what? That's the half-life. So if it takes 1 minute to break down from 50 grams to 25 grams, that means that the half-life of uranium is what? That is 1 minute. You can convert it to seconds. 1 minute is 60 seconds. So if you have, let's say another radioactive element contains 1,000 atoms. It contains 1,000 atoms. So when it now breaks down and after some time, you discover that it reduces to 500. So 500 is the half of 1,000. The time taken for it to reduce from 1,000 to what? 500 is the what? That's the half-life of that substance. That's the half-life of that. It's just as simple as that. It's not hard. No, it's not hard at all. No strings attached. And then there's a kind of formula which I've been using over time that you can use for any question they want to ask you in UTME specifically. You can use it to solve any type of question and you get your answer. So I'm going to put that formula on the board very soon. So, but before I go into that, I mentioned natural and artificial radioactivity the other time. So under natural radioactivity, as you have on the board, we have different types of them. There is alpha emission, there's beta emission, and then there is what? Gamma rays. That is to say, if you have a substance and that substance is undergoing natural radioactivity, it breaks down spontaneously. That is to say, it breaks down by itself, and then to give either of these what? Three things that are on the board. So going forth, looking at number one, which is alpha particle, alpha particles and emission. So how do we have alpha particles? Alpha emission happens when you have a radioactive substance. It degrades spontaneously and then releases an alpha particle. So it breaks down by itself, and then in the long run, okay, let's say uranium breaks down now and then forms another substance. So after that substance, which is the daughter nucleus, daughter, Daughter, which is the daughter nucleus, it will still release an alpha particle. Now, what is this alpha particle? Alpha particle is what? Helium nuclei. Helium nuclei. Helium is the second element, like on your periodic table. Hydrogen, helium. Helium nuclei. So, and I explained the other time about nuclei. The nuclei, they have what? A characteristic mass number and atomic number. So when you find any disintegration or any emission whereby you have a substance degrading to form another thing, and then in the long run you find helium nuclei being formed, that is a kind of what? Alpha particle. Now follow me and look and check what I'm going to write here now. So let's say you have a radioactive element X. So the mass number is represented with A here, and the atomic number with Z. So this is the mass number on top. This is the atomic number Z here. So if it undergoes natural radioactivity, now the type of natural radioactivity we are talking about here is what? Alpha emission. So it's going to give, this radioactive element is going to give what? A daughter nucleus. That is another thing after it has broken down, and then with the release of what? Helium nuclei. So helium nuclei is the alpha particle that we are talking about. Now let me put here. This is the conformation, like this is the configuration 4, 2. The mass number is 4. The atomic number is 2. Now, if this one is A, like X, and you have mass number is A, and atomic number is Z, and in the long run, it will release a daughter nucleus, that is another element with helium nucleus. That means what should be, you can calculate the characteristic. Let me represent the daughter nucleus that you are going to get as Y. That means you can calculate you can get the characteristic mass number of the daughter nucleus and the characteristic what? Atomic number of that newly formed nucleus. So if this one is A and this is Z, and then you are releasing helium nucleus or the alpha particle that is being released, that means bringing your mathematics into this thing now. What will this one be? This one will be, if this place is A, and then in the long run here, you are having this helium nuclide, you are having 4 in this place. That means whatever you have here, if you add it up with this thing, you must get A. So the summation of what this place, what you have here, the mass number of this nucleus, with this thing, with this helium nuclide there, the mass number here, you must get A. Now moving to the down part, this is Z, which is the atomic number. So if you are adding 2 here plus the atomic number of whatever you have here, you must get Z. So how do you do it? So if this place is 4, that means this place will be what? A minus 4. If you add A minus 4 plus 4 here, that means you get A back. This place will be what? Z minus 2, following the same principle. So if you add this to this, you get Z here. So basically, what alpha emission is about is that a radioactive substance degrades, and then what? Alpha particle is being released. Alpha particle that is being released is what? Helium nucleus. And then the daughter nucleus that you eventually have, its mass number will reduce by 4, while its atomic number will reduce by what? By 2. So if you have, okay, now let me just assume, let's say this uranium. Let me just assume that this is uranium. Uranium is the radioactive element we are talking about. Let's say it has mass number 238 and atomic number 92. Undergoing natural radioactivity. The one we are talking about here is what? Alpha. Under natural radioactivity, we are talking about what? Alpha emission. So the element that you are going to get now, the mass number is going to reduce by what? 4, and the atomic number reduced by what? 2. And then in order to make 4, or to make sure that what you have on the left is balanced with what you have on the right, there will be alpha particles being released on the what? On the left, such that the numbers will add up and form the substance that is undergoing radioactivity. So let me assume that, okay, we have, okay, let me say this one is just thorium. Thorium is being released there. So what will be the mass number of in this place? The mass number reduced by 4, which is 238 minus 4, which is what? 234. The atomic number reduced by 2, 92 minus 2, and that's what? 90. Now, don't forget the signature of alpha emission, release of what? Alpha particles. And what's that alpha particle? Helium nuclei. So just add helium nuclei. He4 2. Add this together, 234 plus 4, you get 238 back. 90 plus 2, and you get what? 92. So that's the way alpha emission, that's the way it works. So at the end here, you still have energy being released. You have energy being released. So that's what alpha emission is about. So when you have a substance undergoing alpha emission, what happens is that that radioactive substance degrades into another thing, whereby that other thing that is being formed, the mass number reduces by what? 4, and then what? The atomic number reduces by 2. Mind you, they might give you a question and say that, okay, let's say radioactive element X with a particular mass number and a particular atomic number undergoes 4 different types of alpha emission. You know, this one is like a single alpha emission. So if it undergoes 4, that is multiples like in 4 times. That means whatever you have here, you multiply it by 4. So if it first undergoes the first alpha emission, that means the mass number reduced by 4, the atomic number reduced by what? 2. So if it does it 4 times, that will be what? 4 into, you know that normally the mass number reduced by 4, the atomic number reduced by 2. So that means eventually the mass number is going to reduce by what? 4 times normal one that is supposed to be 4 times 4. Mass number reduced by 16. Then the atomic number reduced by 4 times 2. And that's what? That will be 8. So if they give you, like, they give you a question whereby you have to multiply, having understood the basis, you'll be able to attempt it. So it's not hard at all. So it's very simple. So at least this is like this simplest part of nuclear chemistry you can never find anywhere. So now that's about alpha emission. So there are some characteristics of alpha emissions. I don't know if you try to read if you have read very well, or like after now you can still go and read more, you'll be able to know those characteristics. But I can give you one of those characteristics is that alpha particles, they are like they are positively charged. They are positively charged, although they are light. They are light, but they are positively charged. So, and then another characteristic of alpha particle is that they have high ionizing power. They can really ionize substances. They can cause fluorescence. So another characteristic is that they have low penetrating power. They have low penetrating power. So they are not high energy particles. They are not high energy particles. And then they can be stopped. I know this one is very common. They can be stopped by what? 18 sheets of paper. So if you have natural radioactivity like occurring here and it's alpha emission. So, and then you have rays. Oh, sorry. You have energy being released and then alpha particle being released. So it can be injurious to you. But if you use a sheet of paper to block where that thing is happening, like those emissions cannot reach you. So they can be stopped by a thin sheet of paper. They can be stopped by a thin sheet of paper. So if you are in your lab and you are doing something that has to do with alpha emission, and then you wear your lab coat, so I can say to you that you are safe because the thickness of your lab coat is more like compared to that of the paper. So alpha particles, they can be stopped by a thin sheet of paper. And then one very important point about them is that once alpha emission occurs, so the mass number of what you are going to get eventually will reduce by what? 4. The atomic number will reduce by what? 2. And then helium nucleus will be what? Liberated. Helium nucleus will be liberated. That's the crux of alpha emission under natural radioactivity. So in like 1 minute, let me quickly talk about half-life. So I wrote half-life the other time. I defined it as the time taken for a radioactive element to degrade into half of its initial value. So there is a formula that is general for it. So this is the formula: nr over n naught equals to half raised to power small n. This formula, if well used, you can use it to solve any questions on half-life. So I've checked like a lot of JAMB past questions, and I'm seeing that this one this kind of thing has always been occurring. So now let's define the terms here. This nr is the amount remaining. That's the radioactive substance we are talking about. nr is the amount remaining after some time. Let's assume this is a radioactive element now. So the mass of this thing now that is n naught. The mass that it has now after it has not degraded at all is what? N naught. Now after some time, it will be degrading little by little, gradually. After some time, it will degrade up to a point that the mass that you have will be less than the original mass of this thing. So the amount remaining after some time, that is what? nr. The initial amount present at a particular time is what? N naught. Let me now say that, let's say the half-life of this thing is what? Is 2 days. And the initial mass is 50 grams. That means N naught to be what? 50 grams. So half-life is 2 days. That means that is to say at the end of 2 days, this thing must have degraded into what? Half. That means if you cut this thing into 2, like half of it must have degraded. So that means that after 2 days, the amount that will be remaining will be what? 25 grams. If this is 50 grams by mass and the half-life is what? 2 days. That means after 2 days, this one will reduce to half of its value, which is 50 divided by 2, and that's what? 25. So now let's continue it. After the next 2 days, so before the mass was 50 grams, after 2 days it reduced to what? 25 grams. So after the next 2 days, that means that 25 grams that is remaining will still reduce by 2, and that will be what? 12.5 grams. So the technique is simple, just understand the concept. So now let's say the initial mass is 50 grams, and then okay, let me ask you, let me illustrate this kind of thing. They give you a question and they ask that, okay, a radioactive element has a mass of 10 grams. A radioactive element has a mass of 10 grams. So they now say that after 3 days, the mass reduced to 5 grams. Do you know that you don't need any calculation to get the answer? If they ask you for the half-life, they now ask you that what is the half-life of the radioactive substance? Let me say the question again. A radioactive substance has a mass of what? Has a mass of 10 grams. So after 3 days, the mass reduced to what? 5 grams. What is the half-life? I'm glad to tell you that the half-life is just 3 days, because it's the time taken to what? For that radioactive substance to reduce to what? Half of the value it was before. So if something is 10 grams and then it reduced to 50 grams, it reduced to 5 grams, that means it's reduced by half. So that time taken for it to reduce by that half is what gives you the what? Half-life. Now, going back to this, there's something, this small n. This small n is the number of half-lives. Number of half-lives. Small n. So, and it has a formula. So it has an equation. So an equation that combines it is n equals to T over T half. Whenever you see something like T subscript half like this, they are talking about half-life. So this capital T is like a time after, okay, let's say you have a substance now and the half-life is 2 days. Maybe they now say that what will be the amount remaining after 1 day, or any time apart from the half-life. That's what this capital T stands for. So if they ask you a question and be like, the half-life of something is 1 day, how much will remain after 20 days? That 20 days is what this capital T stands for. That half-life is what this capital is. So half-life, the symbol for half-life is what? T half. So if you are to calculate the number of half-lives, it will be that capital T over what? T half. So now, okay, so this one, N half, is amount remaining after some time. This N naught is the initial amount present. Are you getting me now? So this is half, and then this is N. So now let's say, let me give you like just a question. Let's say a radioactive substance has a mass of 10 grams. So that means N naught is what? 10 grams. Now, the half-life of the radioactive substance is 2 days. That means T half is what? 2 days. So the question continues. Now say that, okay, how much of the radioactive substance will be remaining after 2 weeks? That means they want us to calculate this NR. So NR is, that's what we want to calculate. They said how much of it will be remaining after what? 2 weeks. That means our capital T is what? 2 weeks. So your capital T is what? 2 weeks. Now, the half-life is being expressed in days here, but in this place it's being expressed in weeks. So there should be a kind of uniformity. So it's either you convert both of them to weeks, or you convert one of, like, just let them be in days. So let's convert to days. 2 weeks, like, you know that 1 week, in a week you have 7 days. So 2 weeks will be what? 14 days. So this one is the same thing as what? 14 days. 14 days. Now, they ask you to calculate the amount that will be remaining, and that is what? NR. Slot in everything you have. Substitute your parameters. So what is N naught? N naught is what? 10 grams. So come here, it will be what? NR over 10 equals to half. Then you can calculate this small n, which is number of half-life. This is the formula. So our T here is what? 14. And the half-life is what? 2 days. So N will be equals to what? 14 days over 2 days. And that's equals to what? 7. So that means in this place, it will be what? 7. 7. Mind you, in your JAMB, they will not be giving a scientific calculator. But you, with your knowledge of indices in your secondary school days, you should be able to solve this kind of thing without a calculator. So that means you can continue. Is NR you want to get. So that means NR, here, NR over 10 equals to, you can express this in indices. It means what? 1 raised to power 7 over what? 2 raised to power 7. You know when you have something in a bracket and then it's raised to a power, that power will affect everything. All true. So this one, NR over 10 is equals to 1 raised to power 7. 1 raised to power anything is what? Is still 1. That would be what? 1 over. What is 2 raised to power 7? That's 2 times 2. 2 in 7 places. So 2 raised to power 5. 2 raised to power 4 is 16. 2 raised to power 5 is 32. 2 raised to power 6 is what? 64. And then that means 2 raised to power 7 is what? 128. You don't need a calculator to do that. Just so this will be what? 128. Find NR, cross multiply. That means 128 times NR equals to what? 10 times 1. So that means 128 NR equals to 10. So your NR, which is the amount remaining, equals to what? 10 over 128. Reduce this to the lowest term. 2 can go in 5. In 10, that's 5. 2 in 128, that's what? 64. So now, this will be the amount that will be remaining after what? 2 weeks. So it doesn't matter how they frame the question for you. You knowing this formula and understanding what each species in this formula represents, you'll be able to what? You'll be able to maneuver your ways through any question that they give you. Something like this. So it's not a complex process. So you understanding the question, understanding the formula, and everything in it. So it's going to help you to solve any question whatsoever they bring under half-life. So when they say half-life, they just give you any question, just use this law. JAMB syllabus will never go beyond something that you can use this law to do. So it doesn't, irrespective of the question you are being asked, once you are able to get those things inside this law, you are free to go. So you can do something like this. So now that's just a little about half-life. That's a little about half-life. Don't forget, under natural radioactivity, we started with alpha emission. We continued with beta particles, excuse me. So, and then we continue with gamma rays. So in this place, we've talked about alpha emission. Alpha emission. And don't forget, I told you that alpha emission is a type of natural radioactivity such that a radioactive substance breaks down, liberates alpha particle. What's an alpha particle? Helium nucleus. And then the daughter nucleus, that is what you get in the long run, the mass number is going to reduce by 4. The atomic number is going to reduce by what? Going to reduce by 2. So, having done the introduction to radioactivity, we'll be able to talk about natural radioactivity and then alpha emission. And then we've been able to talk about half-life. So that's for that's what we'll be doing now, like currently. So, but after now, I still have other things that I want you to know. So I want to keep you guys updated. Make sure you follow through, as we have like more, like much bigger things to present to you. In the next class, I'll be taking you beta emission under natural radioactivity. So I want you to come prepared. So as you have a lot to gain from the class. I remain Folaranmi Israel Olaoluwa. Thanks for your time.
Be sure to link up with us and message us and seek out for our email, send us messages for further questions and mentorship after you have seen these videos. I'm very happy to say this again, that it's a time for you to move on and succeed. It's a free success project 2025. Bless you everywhere that you are. Again, my name is Emmanuel Aderoju Adeyemo from Creative Minds Royal Concept.